All right, let's jump right into this explainer. Today we're going to completely demystify a term that honestly haunts a lot of math textbooks but is actually brilliantly simple: real numbers. We are stripping away all that heavy jargon to look at the visual, logical core of what this actually means. You know, you've probably heard those super complex textbook definitions before, right? But let's just step back and ask the most fundamental question here. What exactly makes a number real? When we use that word in everyday life, we mean something that, well, physically exists. In math, it's not entirely different, but it has a very specific set of rules. So let's bypass those dense, boring paragraphs and get straight to the most direct answer.
Here is the absolute simplest definition you'll ever need to remember, and it relies on something you probably learned way back in grade school: the number line. A real number is, quite simply, any number that can be plotted on a standard number line. That's the golden rule. If you can find a spot for it, with positive numbers stretching out to the right of 0 and negative numbers stretching out to the left, then boom, congratulations, you're looking at a real number. It's really all about just having a specific address on that infinite path.
Section 1. Plotting the familiar and the weird.
Okay, let's start really simple. Take -2. It has an exact, undisputed location right there to the left of 0. So yeah, it's definitely a real number. Integers like this are basically the most well-behaved citizens of our number line. But what's really interesting is when we start to challenge this rule just a little bit. Like, what about 0.5? It's not a whole integer, right? It represents a fraction of a whole. Does stepping into the world of decimals somehow break our simple visual rule?
Well, of course not. 0.5 might be a fraction, but it slots perfectly midway between 0 and 1. You can literally point your finger right at it on the line, so it is firmly a real number. So far, our plotting rule is holding up perfectly.
Let's crank it up and look at something a bit more chaotic, though: the square root of 2. If you punch this into a calculator, you get 1.414 followed by, well, a whole bunch of other numbers. Those digits just do not end. It's what we call a non-terminating decimal. So how on earth do you plot a number that never even finishes calculating?
I mean, it sounds logically impossible, right? But here is the fascinating truth. Even though our human way of writing out the decimal literally takes forever, the number itself actually exists at a very fixed, specific geometric point right between 1.4 and 1.5. Because it has a solid home on the line, root 2 is absolutely a real number.
And honestly, this brilliantly illustrates why the incredibly special number pi, which is roughly 3.14159 and famously goes on to infinity with its non-terminating decimals, is a real number too. It isn't just some magical floating concept, it's an actual value with a precise coordinate just slightly past the number 3. Because pi can be plotted firmly on the number line, it falls perfectly into our definition of a real number.
Section 2. The 3 types of decimals.
Okay, so to bring some order to this, every decimal you plot falls into one of 3 distinct personalities. First, you have your terminating decimals, like 0.375, which just politely stop. Second, there are non-terminating recurring decimals, like 0.666, where the 6's repeat infinitely in a strict, predictable pattern. And third, you have the wild ones, non-terminating, non-recurring decimals. Like our old friend root 2, these are infinite strings of digits with absolutely no predictable pattern whatsoever.
Section 3. Rational and irrational numbers.
So here's where it all comes together. Those first 2 orderly categories we just talked about, the terminating and recurring decimals, they actually bond together to form what we call rational numbers. That leaves all the chaotic, non-repeating, non-terminating decimals grouped entirely by themselves as irrational numbers. And that right there is the true fundamental difference between these 2 famous families of numbers.
Which leads us perfectly to the second, more formal definition of our topic today. If you take the entire family of rational numbers and you combine them with the entire family of irrational numbers, together they form the complete, unified set of real numbers. It is just so cool how the visual number line rule and this formal algebraic definition map perfectly onto the exact same reality.
So what's the big takeaway for you here? Well, it proves that math isn't just a random collection of disconnected rules. Whether you picture a physical infinite line or you combine the logical families of rational and irrational numbers, you arrive at the exact same beautiful truth. Any plotted number is a real number. It's a perfectly consistent system.
But as we wrap up this explainer, I want to leave you with one incredibly provocative thought. We've clearly established that every single plottable number, no matter how weird or infinite its decimal might be, is completely real. So, what kind of bizarre, mind-bending mathematics happens when we encounter a number that physically cannot be plotted on this line at all? If the line contains all the real numbers, what exactly lies entirely outside of it? Keep that question percolating in the back of your mind for next time.